In this video, I'm going to show you how to make SAT solving a bit faster by using a rule called unit propagation. So the problem we're going to solve is that backtracking is rather oblivious to the structure of the problem. This is the example formula from the last video, and we can see immediately that B has to be true for any satisfying assignment. But backtracking just tries the atoms in some order and doesn't know that B must be true, so it might try B being false first. And as we see, other forced assignments occur during the search. So for example, we might be in a situation like this, where we have a clause where the first two components have become false by decisions we've made. And this means that if this is going to succeed in any way, the last part has to be true, which means that D has to be false, because we need to make at least one literal in every clause to be true. So using this idea, we can make the search for satisfying assignments a little less naive. So let's look at the unit propagation step. If there is a clause C or A, and the current valuation says that C must be false, then we extend the current valuation with A forced to be true, because that's going to make this true. Symmetrically, if there's a clause C or not A, and the current valuation says that C is false, then we extend the valuation to say that A is forced to be false. And note the A needn't necessarily appear at the end of the clause, it could appear anywhere inside. So let's see an example. So we have this formula from before. We start with the empty valuation, we do unit propagation, which means that B is forced to be true, because this clause has to be true, it's the only one in there, so we set it to be true, and now it's forced. Now we didn't have any more unit clauses, so that's any clauses with one thing left in, so we make a decision. So we decide A is going to be true, and then we do unit propagation again, because now we have two clauses where there's one unassigned literal. And we pick this one, and we're going to say C is going to be false, which will make not C true and make this clause true. So now it's made this clause true. However, this clause is now false, so we have to backtrack. And when we backtrack, we don't change this decision, because it was forced. We change the decision on A, so that gets flipped from true to false, and now becomes forced. Now we do unit propagation again. Now we make another decision. We decide that A is going to be true, so that makes this clause true, and this clause is okay, and now we're left with this one. It's got one literal left, so we do unit propagation, and we end up with this satisfying assignment where B is true, A is false, C is true, and D is false. And in comparison to the previous backtracking only strategy, we had to do 4 backtracks without unit propagation, but only 1 with unit propagation. So in using unit propagation, assuming we can do this very quickly, we can save a lot of time. In a special case where if every clause has at most 2 literals, then unit propagation can mean a lot less backtracking. So here's an example taken from package installations where we want program A1 or program A2 installed. If we decide that program A1 is to be installed first, then unit propagation can now just take over. So this is going to mean that program A2, to make this one true, program A2 has to be false. And now we've got 2 other ones where we can do unit propagation, and following this through all the way, we immediately just use unit propagation to find the satisfying assignment just from our first decision on here. And it might have been this was wrong, we had to go back and do this one. But this at least means that we don't have to do any backtracking after we make our first decision. So if every clause has at most 2 literals, then unit propagation means that we have at most 1 backtrack. This means we can solve the problem in polynomial time. Normally we might need 2 to the n backtracks, but in this case we have to most 1 backtrack, and all we have to do is trace through the problem. So if the n-SAT problem, if n is less than or equal to 2, then there is a known fast polynomial time algorithm. If n is greater than or equal to 3, there is no known general fast algorithm. So this is an interesting divide in the complexity of these problems. So a quick summary of the rules. So these were the rules for finding a good assignment. So maybe we have a valuation that doesn't say anything about A, we just decide it's going to be true. Or we have a valuation that doesn't say anything about A, and we just decide it's false. And if we found a good valuation, so a valuation that makes all the clauses true, then we return SAT for that valuation. But if we don't make lucky enough guesses, we're going to have to backtrack. So if we have a valuation that somewhere in the middle has D decided to be true or false, and the trailing valuations are decision free, then we backtrack, set A to be the opposite. So if it was true, it becomes false. If it's false, it becomes true. And now we set that to be false. And if we have a decision-free valuation, but it still hasn't worked, then we are forced to return unsatisfiable. And the two unit propagation rules, either we have a clause which has one unassigned literal and the rest of the clause is false, so we must set that to be true, or we have one unassigned negated literal and the rest of the clause is false, so we are forced to set it to be false. So what I've shown you is a relatively basic SAT solver. The unit propagation rule does make things fast, but real SAT solvers pull a number of other tricks. So one is to use very efficient data structures, and the key is very fast unit propagation. The other key is to use heuristics to guide the search. So which atom to try next, so not just A, B, C, D in order, but we might have heuristics which try to select which looks like the most likely atom to expose the most amount of unit propagation in the next step. And similarly, whether or not to try true or false first. They also incorporate additional rules. So one such thing is called non-chronological backjumping. So we can skip over several decision points by analysing conflicts. This means that we look at the reason why a clause became false when we are forced to backtrack, and we undo several decisions at once. And also clause learning to avoid doing the same work over again. So when we skip over these conflicts, we add a clause to the set, which means that unit propagation will make sure that we never do that, never go down that blind alley again. And combined, these are called conflict-driven clause learning. Another possible algorithm is a random walk between possible valuations. And this works better when the problem doesn't have much regular structure. So this is the kind of problems arising from some physics applications. So there's some further reading. This blog post has a simple Python implementation of a SAT solver, and it's worth stepping through if you're interested in how to do very efficient unit propagation. This blog post has a bit more formalism on the Boolean satisfiability problem and how it relates to some other problems, and has lots of links for lots more details. And for more breadth and depth than you could possibly ever imagine, then this book, it's a whole book, but really it's a subsection of the art of computer programming, has lots of information about different algorithms and how they compare when tested on many different examples. So in summary, the unit propagation rule speeds up SAT solving by using the structure of the problem to guide our search. And this makes 2SAT very fast. Real SAT solvers are very sophisticated by now. But we won't be covering the sophistication parts in this course.